It's a fascinating piece of work that challenges our long-held belief and understanding about how continents on Earth were formed. Research from Curtin University, recently published in Geology, concludes Earth was hit by comets as our solar system passed into and out of the arms of the Milky Way galaxy. Lead researcher Professor KIRKLAND joins me now. Professor, how did your team arrive at this conclusion?
Thanks very much for the interest in our research. Yeah, so we've been interested in the age of rocks for a very long time here at Curtin, and we've got a range of analytical kit we've been using to date material from all around the planet. And from this massive collection of information, we've noticed patterns within it. So it's really from this big data and the patterns that are held within it that we started to infer these larger scale processes that have affected our planet.
Well, it really is fascinating stuff. So within the scientific community, how has this work been received? Because it certainly does turn traditional thinking on its head that external and not internal forces shaped our world.
Yeah, that's absolutely correct. So as geologists, we normally think of processes internal to the planet, creating the crust we live on. So it is a little bit of a controversial theory, but I guess just, we look up at the moon and we can see a cratered surface, and Earth has obviously seen much more craters and much more impacting events than the moon, simply because we're a much larger mass. So we've got a larger gravity well and more material falls in and hits our planet. So it's a controversial theory, but it explains quite a lot of observations we have.
I mean, it conjures up amazing imagery, doesn't it? What would have been the result of those comet impacts on Earth? What exactly did they do to our planet?
Yeah, so cometary impacts, that's a massive amount of energy that's being instantaneously transferred into the crust of our planet. So you can imagine a fireball coming in, hitting the surface of the planet. And what that does is it excavates a large volume of material from the crust of the planet. And what happens when you excavate a large volume of material? It's very much like undoing the cork of a bottle of soda or a bottle of fizz, and you have what's known as decompression melting. So massive volumes of liquid rock would rise to the surface, and that's what solidifies and produces new crust. So the data sets that we have tell us about a shallow impacting process, and that's what we use to infer this periodic bombardment of our planet roughly every 200 million years.
Was this idea of linking land masses and their mineral resources with the passage of the solar system a new direction for science, or does it actually build on previous work?
Yeah, great question. So there's actually been quite a bit of work already that points to periodic mass extinctions due to cometary impacts on roughly the same sort of frequency. The thing with dealing with mass extinctions is we're limited to obviously only when there's visible life forms or fossil record. So by looking at the mineral record, we're able to go much further back into what we know as geologists we call deep time. So we're looking 3 to nearly 4 billion years ago into the deep time of our planet and relate that back to these processes of crust production. So there has been ideas already, but we're really extending that information into the formative history of our planet.
So where to next for your team? Are you continuing this core research, or is it taking you in another, controversial, radical direction?
Yeah, so I think one of the things we'd like to do is look and see if we can see this similar periodicity, the similar timing on other pieces of crust. So we would like to go to other cratons, other old bits of the planet, and see if we see a similar signature. But also we'd be very much interested in looking and seeing at the lunar surface and dating bits of the moon to see if we can see this similar periodicity, which would help to shore up this quite controversial theory.
As technology improves, machine learning matures and quantum computing takes hold, can we expect our understanding of the cosmos and our place in it will continue to evolve?
I think absolutely. So we're already dealing with large amounts of data produced over many years, and that's what helps us see this pattern, this timing, this frequency of events. But we're also trying to link that into different subject areas. So we're thinking about astrophysics, and looking at, quite complex simulations of how the solar system orbits the galaxy. So we're trying to link in these very different data sets to each other, and that really helps when we've got large computing power.
Fascinating conversation, Chris Kirkland from Curtin University. Thanks so much for sharing your research work here on the APAC network.
Yeah, pleased to talk to you. Thanks very much for the interest in the research.